Good morning. Let me just adjust my camera, make sure it's in the right place. Or good 9 a.m. to you, Andrew. Don't people just say good day around the middle of the day? We're kind of Australian, so we probably don't say good day. We probably say g'day, maybe? Do people even say g'day anymore? It feels a little slightly old-fashioned. I'm not sure. Anyway, for those of you who aren't Australian, because I know we've got a significant percentage of international students, there's a lot of sort of stereotypes about Australia, and one of them is that we say g'day, g'day, and I know some of us do, but not everyone does. It's like one of those things where, you know, the view of a country from the outside is always a little bit different from the genuine view of a country. Like, in general, when you live somewhere, everything sort of feels normal, and from the outside, it's kind of like, what image has the world built up of a country from the outside? And that can be sometimes, when you think about it, it can be like 20 years out of date or something like that. It can be like slowly catching up to how the country actually is, depending on how much the country goes out into the media. I think certain countries, everyone sort of gets a pretty good picture of what's going on. So in Australia, you get a really good picture of what's going on in the USA because we consume a lot of their media. So we see all of their TV shows and even a lot of their news and things, because they're, I guess, media-wise, they're the most dominant country in the English-speaking world. Whereas the amount of media that Australia puts out to the rest of the world is much lower in comparison. So people may only have a small idea of what's happening, and and you get this funny thing where we tend to claim New Zealanders. So anytime there's a New Zealander who is successful, the world thinks that they're Australian, and Australia never does anything to disabuse them of that notion. Like, we claim Crowded House. Who else did we claim? I think we claimed Mel Gibson and Russell. Wait, no, Russell Crowe is actually Australian. No, I think it was Mel Gibson who we claimed, who's also New Zealander. We kind of claimed Flight of the Conchords as well. So there's lots of different things that we as Australians have just said, oh, you know, it's only a little bit of water between us. Let's not think about the big deal about this, like, whole different country with a different government. We're just going to claim those New Zealanders as if they're our own. How's everyone doing this morning? Wait, Riley's saying Russell Crowe is actually New Zealand. I can never remember Russell Crowe and Mel Gibson. They occupy the same kind of niche of Australian movie star, and I can't remember which one of them's from New Zealand and which one isn't. Checkmate or checkmate, mate. Oh, Riley is reminding me that Russell Crowe is actually a New Zealand citizen. Another little thing, I've switched my stream settings to be a much lower latency, so the chat should only be a few seconds behind me now. So it's, rather than like sort of the 10 to 15 seconds before, good afternoon, David, it's definitely the afternoon somewhere. Yeah, so with a little bit less latency now, if I'm watching chat, I might be able to get conversations happening a little bit better. I don't know if anyone noticed, I did an impromptu stream on Friday night, and it was just a relaxed hangout where we just talked about things. There wasn't any subject matter in it or anything like that. This was after I was hanging out on Daniel Mansfield's stream, so those of you who know Daniel Mansfield will know that. So we had this evening where he streamed, I think he finished around 9 or 10, and then I streamed for the next few hours, and so we had both of us just social streaming with our cats and things like that, and I was showing people some of my miniature painting and stuff like that. So I'm not sure if people are super interested in that kind of thing, but we may do more of it just for fun. Week 6 also, oh, this is like more official things are happening at the moment. Next week is your flexibility week. So flexibility week means that the university itself will never deliver anything that is accessible during flexibility week. So I'm going to be giving a talk on what it means to be a computer scientist in a professional sense. So it's not about what's in 1511 or what's accessible in 1511, but I consider it to be the kind of advice that will last a lot longer than that. Actually, it's the kind of advice I give to people who are graduating, actually, and there's the kind of advice I even give to people who are already working about how to be fulfilled in what you do is one way you could look at it. How to actually get hired by people is another way to look at it. How to survive and make sure that computing is like a long-term career for you. So it's all those kinds of things. I might also do a revision session as well, where I do a stream that kind of takes everything that we've done so far and we just do one big example. So as opposed to the code examples I've been doing that are usually with theory in a lecture, so they're like at most 45 minutes of coding, this will be like maybe 2 hours of just like one big example, and we can just do some Q&A and maybe help people with assignments and stuff like that. So it's harder to help with assignments because I don't really want to broadcast specific assignment help. It's not entirely... I mean, we might do it anyway. We'll see what kinds of questions we're getting, and some questions I'll tell you to take it to a forum where you can get a private answer or something, or whether I can actually broadcast something. So someone just tells me, how do I solve stage 2? And then I spend an hour doing the code for stage 2 live. That would probably not be the best idea. that would take the opportunity to do the code away from most people. But yeah, so I will let you know what we're going to do in week 6 as it goes along. We've also got one of the other lecturers, Carol Morgan, who is a teaches a lot about the sort of, I guess you'd call it a bit of the theory of how to think about programming as you're programming it. This is really, really useful stuff about how to structure your code so that you fully understand it. So it's really, really interesting. He's going to give a video to us that you can watch, and I'll release that. Well, I think he's already got it publicly available, but I'll let you know about it so that maybe you can watch it in week 6 when you've got less on. We're highly unlikely to do a 9 AM lecture in week 6, but we're much more likely to be doing an afternoon session or two, seeing how we go. Oh, Alec is asking who won the Warhammer. I think you're talking about between me and Dan Mansfield. We haven't actually played any Warhammer yet. People are talking a little bit about the weekly test. Just be careful. Don't spoil it. Like, you can talk roughly about the weekly test, but don't talk about the actual specifics of the questions, because we don't necessarily want people's chance to do the weekly test to be spoiled by already knowing what's happening. Yeah, and people talking about the lab as well. Okay, don't worry too much about that. If you haven't done your lab yet, obviously only a small percentage of people have labs on Mondays. So let's go into the content itself for today. So today I've got a few things to talk about. One of them is something that you may already have been working on. I usually try to find a good time in the term to start talking about this, and I think now that you've had the assignment for a week, it's a good time to start talking about how we dig ourselves out of holes. Because when we're programming, we can get ourselves stuck in some places where we hit a point where we really don't understand what's going on with our code anymore. And so today I want to talk a little bit about debugging, which is the removal of bugs from the code. Bugs are a term that we use in computer science to refer to errors in the code or things that the code is doing that we don't understand that it should be doing differently. And we're also going to introduce a new variable type today. But let me go through. I have a bad habit of talking about what I've actually got slides on with, and I forget to actually go into the slides. So let's talk about what we learned last week. We talked about arrays. So there was one little detail that we talked about, was that arrays cannot change size. So once the program has started running, and it's actually even technically before that, it would be once the program is compiled, your arrays are of a fixed size and they won't change after that. So I was talking about the subtle detail that you can't use a variable as the size of an array, because then your computer doesn't know how much memory to assign to that array before the program starts. And that's just one of the ways that C works, where it says there's only a fixed size for each array. There are other other programming languages that can do different sized arrays. They're not really technically arrays if they can do that. But in C, there's only the fixed size for these. We will actually be looking later on at a different data structure known as a linked list. And I've talked about that a little bit. I've mentioned it, but I haven't really gone into it because we're not going to go into it until we have the tools necessary to understand it. And that thing can change in size, but for now we're going to use arrays that don't change in size. We also looked at two-dimensional arrays. I have a feeling that everyone who started working on this assignment has probably learnt a bit about two-dimensional arrays by now, because there's a fair bit of that going on. If you haven't, there's some help in this week's tutorial and lab to go deeper into the two-dimensional arrays. Wait, Michael's asking what time is Mark starting. Did you mean the lecture, or? Oh, right. Someone had their YouTube on pause and they were wondering what time I was starting. Yes, it's already started. Oh, Catherine's asking about the presentations that are in week 6. Everything that I'm doing in week 6, even if week 6 is a flexibility week, anything that I'm doing that could be of help to 1511 students, I'll put on the 1511 webpage. So all of the stream links and things like that. If I'm doing just a social chill hangout stream, I probably won't put it on the 1511 website, because I want to make the 1511 website just what people kind of need to see. But if I'm going to do a social thing, I will probably just make it a public thing on YouTube Live. So I guess you have to subscribe. I don't want to make people subscribe. It feels like I'm monetizing my students. But also the social thing's not really necessary either. So apparently when I flicked the stream on Friday night, a couple of the different group chats that people had for things popped up. I'm not sure if there's any other way that I would publicize it, because it's not really an academic thing. But you know, oh no. Smash the subscribe button, ring the bell. I don't know who said smash the subscribe button first. I learned that from Davey504, this YouTuber, and I think Two Set Violin do it as well. But you know, anyway, I'm sure they all got it from the same place. The other thing that we learnt last week, and this is the one that's more easy. Oh wait, there you go. Callum's slap like, yeah. The thing that's more easy to forget is pointers, because that's not in the first assignment, but it's going to be in some of the other stuff that we're working on soon. So remember that pointers are variables that store memory addresses. So you could nearly think of them as a really, really specialized type of integer even, because they are actually integers, but they also have a bit more information, not just about being integers, but also that they're made to access variables. So they're made to know where a variable is in memory, and also how big that variable is and what format it is. So if I say an integer pointer, that's a pointer that can take an integer from memory and give you access to it. And we looked at some of the subtleties of pointers, how we could use pointers in functions, and that gave us more access to variables that we have. And we also looked at this kind of connection between a connection between pointers and arrays, where the arrays themselves, the variable that is the array, is really similar to a pointer in that it also gives a memory address at the start of the array. And the nice thing about that is that if we give arrays to functions, then the functions actually have access to the array itself in memory, rather than making a copy of the array. Any other variables that we use in functions are always going to be what we call passed in by value, which means that the function will make its own copy of the variable. I have some fans of DB504 and two-set violin there. People saying I need an outro. I think it would be pretty funny if if I got like the whole streamer stuff happening. I noticed that Dan has a green screen setup going on, because I noticed that he had the cutout. So where I've got up in that corner up there, I have a whole, like, my house in the background. I think Dan is maybe hanging up a green sheet behind himself and doing stuff. I don't know, that I like having my shelf of toys in the background though. We've had a couple of conversations about them before. But yeah, I think it could be pretty funny if I throw in a whole bunch of Twitch overlays and stuff like that. I've tried to keep it quite minimal. I am at least trying to keep up a certain level of professionalism of the whole university lecturer thing. But as you know already, because you've been with me for over a month now, that cracks pretty quickly and easily. Lachlan, I am not setting up stream donations. I feel like, again, monetizing my students. There's something really really ethically questionable about monetizing people who are already paying for the subject and need to be here. So we probably won't do that. Sorry, there's a dot on the door. I'm not sure where the dot is. Oh, maybe it's the little hook on the top of the door. So we've got stuff hanging on the other side of the door. Yeah, and then the lecture will constantly be interrupted by donations. Okay, so what are we covering today? I wanted to... Oh, that's weird. I thought I'd edited this slide. Hang on a second. We're not finishing the example from last week because we actually did finish the example. I have a really strong memory of editing that slide already, but obviously I hadn't. Anyway, so we're going to do a quick recap of pointers because I think that it's going to be good for us to at least see the basics about pointers again before we go on to other things. And then we're going to do debugging. I'm going to explain what a bug is and some of the simple ways that we start with them. So the first thing we're always going to do is try to figure out what each problem is. So this is slightly different from the problem solving thing that we were doing before, but debugging and problem solving kind of go hand in hand because bugs are a very, very specific kind of problem that you're going to encounter. So we're going to talk about the different types of bugs and some techniques we can use to remove them. And I think this comes at the right time because now that you're in assignment 1, that would be pretty rough if we're in assignment 2 already. Now that you're in the assignment and you're working on larger sections of code that all connect together and they're all in the same file, the capacity for creating something that you yourself don't understand is much larger now than it was in the lab exercises. When you've got a lab exercise that don't work, so you can kind of throw it as well. Like you can kind of be like, I'm not going to bother with that one. I can still get most of the marks if I do some other things. Or I can just talk to someone else in the lab and see how they did it and say, okay, I'm going to learn something from seeing how they did it. And we'll go back and forth. And then we can, if we hand in the same file, that's kind of acceptable because we're supposed to be working in groups. But when you're working on an assignment, you're on your own. So it's much harder to know exactly what's going on, and that's by design, because generally when we're working alone on larger projects in a professional sense, we're not going to have someone else also working on the same problem who we can just say, how did you do this? We could talk to people about our code, but no one else is going to be able to give us a solution to something. Like, it's very, very rare for a company to pay two people to do exactly the same thing. Even if you have two people doing the same job, you'll be doing different parts of the same thing. So the assignment pushes you more towards the idea that you do have to write original code once you're out there in the world, and so this is why you have to work on your assignment on your own. But now that we're getting to this point, I wanted to give you some of the tools that I use for figuring out what the problems are in my code and fixing them. I should point out this interesting dilemma, I guess, that it's not even a dilemma, it's just a fact of programming, that we tend to spend about 15 to 20% of our time creating original code, creating new code, implementing new ideas, and we'll spend 80 to 85% of our time. This is really rough, but it doesn't actually change. So we spend 80 to 85% of our time fixing the problems we've caused with the original code we wrote. And I think that's the interesting thing, is that people often think that the better they get at programming, the less mistakes they're going to make, and the less time they're going to have to spend fixing errors, and the more time they can spend just creating these wonderful new things. Unfortunately, that's not the case. So, 20 years later, programming, I still spend the same amount of time trying to fix my code. It's still like 80% of my time trying to make it work, and only 10 to 15% of my time creating something new. The only difference is now that I'm expected to create things that are much, much more complex than before. But the ability for us as humans to magically create something in a highly specific logical environment that's correct is not something that you actually generally get better at. The better you get at programming, the harder the things are you're expected to do. So what I'm saying is the skills that you need to debug are skills that you're going to use forever. So there's no magic point where you can say, I have solved programming, and none of the programs I write from here on will ever have any issues in them, because that's sure as hell not going to happen. Okay, the other thing that we're going to cover today is characters. So we've had variables for numbers so far, and we've only had variables for numbers. Now we're going to have variables for letters. We're not going to be doing a code demo of characters today, because what I'm going to do is I'm going to show you the variable type character today, and then we're not going to use it. Not entirely, but I'll show you how we use characters and ints interchangeably. Then, tomorrow, Thursday, you're getting used to my coded way of saying things, where everything, if we're lecturing, it's always morning. The previous lecture is always yesterday, next lecture is always tomorrow. No, on Thursday, when we have the next lecture, we will be putting characters together into arrays of characters that we call strings, and excuse me, that's when we'll do a demo showing you a lot of the stuff that happens with characters. So what I'm going to do today is just present them to you, and then we'll work on them more later. Michael, your comment about donating things got held for review by YouTube. I think there's obviously anyone asking for donations in someone's YouTube channel is always getting held back for moderation. Riley is saying bugs are like Hydra, get rid of one, 2 new ones pop up. It's an interesting thing, there's actually a meme later on today about debugging that says a similar thing as that. Okay, so, a quick recap. I don't want it to be too quick though, I actually do want to spend a little bit of time talking about pointers, because it's important that we refresh this idea in our head. Pointers aren't going away, even though we're not really specifically using pointers in the lectures this week. What I wanted to do was talk about them last week, talk about this week, And then next week we're going to, sorry, not next week. Next week's flexibility week. Week after next, we're going to start using pointers in everything that we do. So I wanted to just keep this in your memory, so the more times I talk about things, the more likely they are to like land in your memory and actually stick. So a pointer is a variable. It is a variable, though, that stores the address of another variable. So it's a variable that knows where another variable is. It doesn't necessarily store any information about that variable, but it knows where in memory that variable is. So it doesn't know what value that variable might have, but it does know whether it's an integer or a double, or after today, once we've got some more variable types, it'll know whether something's a character. So pointers aim at other things, which means we can think of them in this way, that pointers can point at another variable. So we think of them as references to other variables. We can think of them as, if you want to think of it in a physical sense, I'm holding a piece of paper that has an address written on it. And if I go to that street address, then I have access to whatever's in memory at that address. So that's the way we often think about it, is a pointer gives me access to a location, and it's a location in memory that allows me to read some information. One of the nice things about pointers is that we no longer have to pass the variable's value around when we're passing it to functions, but we can pass a pointer around when we're passing things to functions, and that means that there will only ever be one copy of said variable, but there could be multiple pointers to this variable floating around the place. But the nice thing is they will all just have access to the one variable. So if we say there's only one place that we're keeping this particular value, but every function has access to this value because they get given a pointer to this value and they can change it, then we know that we have this kind of master value for this thing, and we're not going to copy it, send it around. So anytime we want to change it, the main one changes. That's if we want to do that. I'm not saying that we're going to use pointers for everything. Some things we are, some things we aren't. As we get deeper into things as well, we'll realize that giving pointers to functions is sometimes much less kind of memory intensive than giving a whole value of something. So if you think about arrays, for example, arrays do this automatically, where if you pass an array into a function, instead of making a copy of the array, it just gives you access to the original array. So if I had an array of like 10,000 integers or something, that's a fair chunk of memory. If I passed that into a function and it was to copy the array, that would mean that function would have to copy those 10,000 integers. And so that might either slow down my program or make it use too much memory and things like that. So some of these things help like that. We're not worried too much, again, I've said this before, but we're not worried too much about efficiency or use of memory here in COMP1511. But if you continue into programming, you will definitely care about these things. Like, we try to use the minimal amount of memory that we need to get something going. We try to make our programs run at a reasonable speed so that we don't do extra work than we need to get the job done. So things like that are things that we will think about in the future. I'm going to mention this stuff in 1511, but not need you to do it. So we've hinted at it. If you looked at Going Electric, which was the challenge exercise for last week. Wait, last week or this week? No, it was last week. No, we've been talking about it last week. And we added an extra challenge onto that to see if people could think about how they could solve that problem in the minimum number of steps, in a sense. And so we've had quite a few people email that in and stuff. I think Tom's been watching those particular emails and buzzing a few people back to talk to them about it, so I think that's good. If you're not worried about it, don't worry about it, because it's a challenge exercise. We compartmentalize these things, so you don't really have to worry about that. Oh, Tom's here now. Good morning, Tom. Yes, I'm giving pointers on pointers. Lucas asked an interesting question. Can we use pointers to return arrays from functions? Luca, I will hold you there for a moment. One thing I'm going to say is, for the moment, you can't. Because when you think about it, if we make an array in a function, and then we were to give a pointer to that array back to someone, the array itself would disappear when the function finishes. Because anything we create inside a function will disappear when the function finishes. Give me a couple of weeks. We will have a way around that soon. But for now, we can't create a function and give a pointer back to it. However, if we were to be given 3 different arrays, and I had to give back a pointer to which of these arrays fits a certain condition, then you definitely could, as long as the arrays exist outside the function. But we will figure out a way, I think by week 7-ish, like the week back after the break, we will have a way of creating something in a function that doesn't disappear. But I'm not going to talk about that now, because that's going to confuse us if we go too deep into things. Yeah, I think Jasmine's asking the same question there. Tom's answering that right now, but at the same time, yeah, there is a way, but obviously one subject at a time. I want to teach you about debugging and characters today, and we will look at subtle and powerful ways to use memory in a whole lecture on its own. Okay. So using pointers, this is the pure syntax of it. Remember that the pointer symbol is the star. So we will use the star, the asterisk, to create the pointer, and then when we're using the pointer, we will also use the star to access the pointer. And so just remember, this is just like arrays, where the star has 2 different meanings. It has a meaning on creation and has a different meaning on use. Just like the square brackets mean creating an array of a certain size on creation, and then when we're using them, the square brackets mean which element of the array are we looking at. So different purposes depending on whether something has been built yet or not. Also, the other symbol that we're going to use along with variables is the and, the ampersand. This is going to give us the address of a variable. And you can think of this 2 ways. The and can be looking at a variable and asking where it is. The other thing you could say is if you put an and on a variable, it creates a value that is the same as the value of a pointer. So it's nearly like putting an and on a variable is like creating a pointer in and of itself, except that pointer is just the value of the pointer. It's not something that exists in memory, but it's a value that can be put into a pointer. So here is the sort of bog standard way that we would use pointers, is we would have a variable somewhere already existing, and in order to create a pointer to that variable, we first create the pointer. So the pointer has the same type as the variable, but the difference that makes it a pointer is we use the pointer symbol, is the star here. So this creates the pointer, and if we want the pointer to be initially aiming at this variable, we say where is that variable using the and we say okay, the pointer can be equal to where that variable is. So we're just adding some stuff on top of the basics of a variable. So if this was just an integer variable, I'd have the integer is equal to a value like here, but instead if it's a pointer, the value it would have will be a memory address somewhere. We can always use null if we want to, if we don't have an address yet that we're going to store in this pointer. When the pointer is already created and we want to access it, we use the star again. So here I've got an example of printing out the pointer. So %p was the ability to look at the pointer itself. So we're not looking at the variable that the pointer aims at or points at, we're only looking at the pointer itself. So the only value that the pointer has is a memory address. So if we do %p, we'll get the memory address of the pointer. If we want to look at the object, the variable that is at the other end of the pointer, we use the star. So the star is like saying, let me look at this address. All right, now I'm going to go to this address. So I use this, the star says I'm going to go to the address itself. I'm going to look at what is in the address. So it's like using, like, I sometimes like talk about the star once we're using it, it's Google Maps. So if the star is on the pointer after it's been created, so when it's created, it just says it's a pointer. After it's created, it's like saying, take this memory address, type it into Google Maps, go to that location, and then look inside the house and see what data is there. That's what we get when we put the star on a pointer. So this is saying we are following this pointer to what it's aiming at, and we're looking at the value of what it's aiming at. So what we're going to get for this second one here, so I'm saying the value of the variable at this location is this. The star is how we access the value of the variable that we're looking at. Pointers can be put into functions as well. I think Tom's clarifying a lot of stuff there. I'm going to leave that with you, Tom. Alright, so one of the most useful things that we can do with pointers is use them as function input. So if we put a pointer into a function, what that's doing is giving us a reference, as it were, to a variable that exists outside of the function. So this is a variable that exists somewhere in my memory that my function is not usually allowed to see, because functions are contained in their own little piece of memory. This gives this function access to something else, which means if it puts the star on the thing, then it can find it and do things with it. And I was saying before, pointers arrays are similar. They're not exactly the same thing, right? Because an array is specifically saying, I have this much memory for this many identical pieces. I can be accessed with square brackets to find particular things in it. Whereas a pointer is generally thought of as access to an individual variable. Having said that, an array is technically a variable, and you could do a pointer to an array, but for the moment what we're going to be working with is pointers to basic objects. We could actually consider a pointer to the start of the array being in use identical to the variable that is the array itself, because both of these contain exactly the same information, which is the memory address of the start of the array. For our purposes, they will be interchangeable, but I'm pretty sure there are some subtle differences between them when it comes down to it. So when we see arrays are sections of memory that contain multiple variables. So if we want to, we can use pointers to aim at each element of that array, and it will see them just as the integer or double that we're using there. But the nice thing about it is that when we give the array variable, so if we don't put the square brackets on the end of the array variable, it gives us the whole array. If we put the square brackets on, what it's saying is I want to look at a single element in the array. So when we give this whole array, this concept of passing a whole array to a function, it doesn't actually give all of the numbers in the array. What it does is just tells the function where the array starts. And then the function has to say, alright, if I know where the array starts, then I can look at the individual elements of the array. We still have to be careful we don't go off the end of the array. Accessing an array out of bounds is still a problem. But the trick being that if we pass an array into a function, we get access to the original array. So we get to use the original array. It's not a copy of the array in the same way that we would get copies of variables. If this is confusing, and I fully understand if it is, because pointers are just by their nature more confusing than other things in C, go back to my previous lecture on pointers where I looked at how pointers and functions work. I think that's a good thing to think about, is like how we pass information into a function is usually by copying the value of that variable and creating a new variable inside the function. And pointers and arrays kind of do that as well, because what they send through is a copy of the value of the memory address rather than the actual memory location. It's only the address of that piece of memory. So it's a bit subtle. It's better if you look at the diagrams, I think. I wonder if there's anything else. Ah, Dean's here as well. Hello, both of you. Looks like, I think with the two of you here, I won't need to answer any questions in chat, so I'll just only hop in there if I need to. Okay, so we're going to look at debugging. Now, if you don't recognize this scene, then there's some education that you need. It's not education. This is the movie Aliens. So Aliens is probably one of the best examples of debugging in real life. It teaches us a lot about the fact that we can go into a program overconfident in our abilities to deal with the problems that come up, and then we find ourselves lacking, and then we can try different solutions to attempt to remove bugs from an environment, as it were, and then we can learn from this movie how hard it is actually to remove bugs from something. So what Aliens is, sorry, I'm just laughing at myself. It's a sci-fi movie about shooting aliens, but it's a hilarious analogy to trying to stamp out bugs in software, because it's very hard to actually do it. Yes, and everyone's saying hydration is key. Now this is my peak hipster mug, because it's a jar that has a screw top, only it has a handle as well, so it's like full hipster. Anyway, this movie was released I think in 1994, so I fully understand if you haven't seen it, but I think it's fun because as a movie that didn't use CG and it's all practical effects and puppets and things like that, it hasn't aged that badly at all, and it's a James Cameron classic, so check it out if you want. I love throwing in ads for things that I'm not getting any commission for or anything. It's just the stuff that I like. Anyway, so classic movie, and this is a line from the movie. I say we take off and nuke the entire site from orbit. It's the only way to be sure. And that's the way we think about bugs sometimes. Okay, so what we're going to talk about now is, what is a bug? So what do I mean by a bug in software? And there are different types of bugs, and we're going to learn about two specific types of bugs that are things that are going to come up a lot of the time in the programs that you're writing in the beginning. If we wanted to class bugs into different types, there would be a few more than this. But for the moment, at the level of programming that we're doing, we're not going to worry about a lot of the others, and these are the basic ones that are going to stop your program from doing what you want it to do. So we're going to look at the different types and how to find these different types. I mean, sometimes the bugs find you, because sometimes you can't even compile your code without it, and we're going to talk about this process of finding out exactly what's causing our bugs and finding out how to solve them. What are we talking about? Charles is saying that we could just delete our entire project and all the bugs would be gone, which is very similar to my viewpoint here. We take off and nuke the entire site from orbit. Taylor is saying, yes, this is a mason jar. I think that's what that thing is called, like the mason jar. If you didn't have a handle, I think it would normally be a mason jar. Okay. Little questions happening in there, but I think Dean's answering those. Okay, so what is a software bug? And at some point they thought of errors in their code being like a bug, an actual physical bug getting stuck in a machine and stopping the machine from reading the holes in these cards. So this is like really old school programming, but I mean, they went to the moon with this kind of programming, so I wouldn't belittle it too much, but I would also respect the fact that we can now program by just typing stuff in on a computer, as opposed to back in the day where they had literally cards, piece of cardboard, and they would have holes punched in them. And depending on where the holes were punched in the card, your computer would read that. So it would read from the holes punched in the cards, store that in its memory, and then do its processing. So imagine if to edit your code, you had to get a machine that would take whatever you were typing and punch it into a card as bits. So every letter that you type needed a series of bits to represent it, and it would have these holes in the card. And then this card would get fed into a machine that would read it and would read those bits. And so it's kind of like, imagine DCC as a compiler being a gigantic machine that you have to slot cards into one at a time, and each card can only carry about, I don't know, 20 characters on it. They got to the moon with those computers. So it's quite impressive. Anyway, it was around that era, I think, where someone first talked about the phrase of bugs, because they had this idea that if there was an error, it could have just been something physical. It could have been a bug in the machine stopping the reader from actually reading the hole in the card. Somehow that term has continued and has stayed with us. I'd have to look that up. I don't know if that's actually the history of it, but I think it's something around that era. So nowadays we think of it as anything that that we have, most likely we have introduced into our code, but sometimes it's like ramifications of code that we're connected to and things like that. But it's any kind of error that stops our program from doing what we intended it to do. It's not always going to be the program not doing what we've asked it to do, because sometimes what we ask the program to do and what we intend it to do are two different things. And this is a pretty common thing, right? Anyone who doesn't fully understand the language and tries to speak in that language is going to make mistakes. And so that's what we are, right? We don't fully understand C. We are not 100% fluent in it. And I say we because I'm not either. There's plenty of C that I don't know, and there's plenty of C I'm still going to make mistakes in. I mean, you've kind of seen this, right? Because every now and then I'll make a mistake in my code, and then like the chat will be like, Mark, you're making mistakes. But I'll just go ahead and compile it, and it will or won't work and things like that. And I'll be looking at it and going, oh, wonder why that happened, you know? Because there isn't a term goes by that I teach this. And this is like, you know, and this is the truth of it. I think it's an important truth to know, that I'm now teaching 1511 for the 5th term in a row, and I still make mistakes in lecture demonstrations. And so I think the understanding is that mistakes are just inevitable. It's not something that we try to stop making mistakes. It's better for us to think about how we correct mistakes and accept that they're going to happen, rather than trying to make ourselves unable to make mistakes. Because it's pretty easy to stamp out all possible mistakes, and this is the same thing of like people ask me why their code doesn't work and I delete all their code. I've never done that, by the way. That would be super mean. But yeah, like we were saying in chat a second ago, if you were to delete your entire program, then yes, there are no bugs. But that's not what we're after. We want to accept that the bugs are going to happen and find ways to remove them after the fact. So at no point in this lecture about debugging am I going to talk about how to write bug-free code. I'm going to talk about how to remove bugs from code we've already written, because I feel like the bugs are in some ways inevitable, and it's better to remove them than it is to try to work without them. Okay, so we're going to identify two forms of bugs, two things that are going to come up the most, and I'm going to separate these two into two different types: syntax errors and logical errors. This is pretty broad brushstrokes, by the way. I think if you wanted to, I mean, we don't do this at CSE, but I can imagine teaching a course that's 10 weeks worth of just removing bugs from code, and I have a feeling a lot of people would want to do this course. Because I prefer to spend 10 weeks learning about removing bugs than actually doing the debugging that I've had to do over the years. It's been much, much longer than 10 weeks, and if I knew everything I knew now about debugging, I would have saved so much of my life. But we don't really have that choice. I don't think that someone gets good at debugging without practice anyway, so I would have had to spend a lot of that time. Anyway, the two error types that we're going to look at, and these are the two that should be understandable to us now. This is why I had to wait until you'd done a fair bit of code before I talked about this. Syntax errors and logical errors. So, a syntax error is a an error specific to the language we're trying to speak, the programming language we're working in, and how its own grammar and setup works. So I think I spoke about this before, that was joking about having an English teacher in high school who will refuse to talk to you unless you speak in perfect grammar, unless you follow the rules exactly. I mean, English as a language is really, really loose. It has so much ambiguity and so much connotation that you could say something that was factually incorrect, but people would understand what you meant anyway. I mean, the whole idea of what a metaphor is, or an analogy. When I talk about a memory address, a pointer being a thing on a piece of paper where you write down an address and being able to go there, all of that's impossible, right? Because this is actually not written on paper. It is written in memory as ones and zeros, and I can't go there because it's at a nanoscopic scale where if I touched it I would probably break it all. So that kind of thing we can still fully understand. Well, it's still pointers, it's not fully understandable, but you know, I hope that people still understand those analogies and metaphors as I use them. But C as a language does not have metaphor, it does not have analogy. It has absolute exact correctness or nothing, right? So us as humans, spending the majority of our lives communicating with each other in languages that have very openness, you know. So if I get 90% of the way there, someone will be able to understand what I'm saying. If I get 90% of the way there with C, that means 10% of it is wrong. And that 10% which is wrong will entirely stop my program from running. You can try this. Just go through a C program and delete every 10th character. I think a human would still have a reasonable chance of understanding what you wrote there, but the computer will throw it all away. It will say, I can't do this, right? So any slight mistakes can completely change the behavior of a program. The easiest syntax errors to correct are ones where you have written incorrect C. So you've just slipped up while you were typing and you haven't seen it, and so you've just gone to compile with code that isn't legal C, or you've forgotten to close a brackets somewhere or something like that. What we will usually do, and these are the errors that I think that you've spent the most time with so far, because these are the just wrangling C as a language errors, and you would have seen these because they nearly always cause compiler errors. So stuff that causes compiler errors, reasonably easy to work with. You work through the compiler errors and you try to solve them. Some of them are weirder. So anything that's a bracket issue, the compiler error may not tell you what's happening. The error message from the compiler might be the consequence of the issue rather than the issue itself. So we're going to talk a little bit about how to find those anyway. The other type of error we have are logical errors. So logical errors are very different from syntax errors, because we could write a program that is perfectly functional C. We can write a program that compiles entirely. So I don't know if I've said this before, but I have a funny saying I say sometimes when I compile a program, is that the scariest thing is that when you first compile a program and it does compile, because that means the mistakes you've made are hidden. Like, it doesn't mean that the program's going to work first go, because I usually don't expect a program to work first go. But if I compile something and I get no errors and I've only just written it, then I'm saying the inevitable human errors are somewhere else. So that means that I have written correct C. So I've written something that follows all the rules of C, all the grammar is correct and stuff, but I still don't know if it's saying the right thing. So this is the idea that a program can be syntactically correct. Syntactically means it follows all the rules, the semicolons are in the right place, every open bracket gets closed, you know, the while loops are properly formed, all of this kind of stuff, but it just doesn't do what we wanted it to do. So I've made a mistake and it just does something else. And that can totally happen. So a couple of different reasons down here. of how this could be happening, we just read the question wrong. So something asks us to do something, or we wrote down something previously saying, okay, the solution to this particular problem is I loop through this array and do this. Only that wasn't the solution. We made a mistake, and we weren't supposed to loop through the array and do something. We were supposed to do something else, and we didn't realize. And so we're just going about the problem the wrong way. Sometimes we solve the wrong problem, which is which is always really funny. I always laugh at this because it's kind of like you give someone a hammer and everything looks like a nail. So if the most recent thing I've taught you is pointers, and you say, okay, pointers are really useful, I'm going to put pointers in everything. Then you can put pointers in a program that really doesn't need it at all. Then you've ended up in a situation where you're not solving the problem that needs to be solved. You're using the new toys that I gave you instead. And programmers, we get caught up in that a lot, because there's so much joy in programming a lot of the time. So there's a lot of joy in being able to get your computer to do things, and doing interesting things, and playing with the most recent concept that you've learnt about. That sometimes we will go off and do something random instead of solving the problem that we're supposed to solve. So that's another thing that we can do in terms of logical errors, is we miss the problem already entirely because we've forgotten why we started writing a program, and now we're thinking about what's cool about a program instead. And the other thing, this is a very human perspective, and this will come up much more later. Our current programs that we're working on, like stuff like Freefall, are going to be tested by machines, so they're going to be very specific. But sometimes we write programs and we forget how the program's intended to be used, and so we make logical errors there. So logical errors are very much the human errors. Not that a human didn't make all the syntax errors that are in your program, but that's much more a mechanical thing. Logical errors can be much more insidious because they can be, we're just not thinking about it right. So, other things like that will happen. So, thinking about how we find the bugs. One of the easiest things, and this is something that you would, I think, all have come up with before, which is the bugs that find you. So the friendliest bugs are the ones that find you, and those are usually the ones that find you from the compiler. So usually syntactic errors will come up as compiler errors, and it's really easy to catch them because they're right in your face. They're not insidious. They don't appear in your code by accident or anything. Well, I guess they do appear in your code by accident, but you're going to see them happening. So syntax errors will come to you quite easily, and so we're going to do at least a quick look at how we're going to catch bugs with a compiler and how we're going to fix bugs with a compiler. When we're looking at logical errors, code reviews can be really handy for that. Because in a code review, someone could just say to you, hey, I don't understand what's happening on line 112. What are we doing there? Because I thought that the problem was to solve this. And then you could look at it and you can say, oh, line 112 and the function coming off that doesn't actually need to be in this program. I think I was solving the problem in a weird way, So getting some help like that works really well. But I do want to give you tools you can use that don't require other people. And so one of those is going to be testing. Testing is super important, and in 1511 we've given you a lot of your tests to begin with. You may notice that we slowly sneak in less accurate and less useful testing as the term goes on. So some of your lab exercises will start to look like they're not auto-testing everything. And so what we're going to be doing is slowly encouraging you to be sure of your programs regardless of what autotest is telling you. Because there is no way that we could make a set of tests that would accurately test every possible thing in your program. You're going to need to be able to do that yourselves. So sometimes out there in the world where we're making software. Sometimes there is a set of tests, and we're just writing software that meets tests. But the majority of the time, we're writing software that meets a specification. So something like freefall, saying, okay, this should do this should do this, and stuff. But not even at that level of detail. It's usually much less detailed than that. Usually someone comes up to you and says, oh, can you make the back-end calculation engine for a vertical shooter arcade game? And you go, yeah, I probably can. Do you have any more details? And they're like, no, of course not. You're the programmer. You go do that. And so it's up to you to even write what's happening in freefall. So what we need to do is we need to figure out what the actual intention is for something and how we then meet that. And it's very important for us to figure out if we have an intention for something and we want to find out whether we met it or not, how do we break that down into its parts and how do we test things? So a lot of what we're going to do to figure out logical errors in some code is going to be our ability to pick apart our own code and find out exactly what's happening. And so one of the most important things is to figure out how your program is actually running and how it does things. Mason is asking about breakpoints, and I think Tom and Dean have answered that. We don't really have the time in 1511 to teach people how to use an interactive debugger. So there are programs we use to debug, and at a professional level we definitely use these. But 1511 is about building up basic concepts. So if I was to teach you how to use one of these debugging tools, you'd probably get caught up in it for a while. We would end up spending sort of 2 weeks on it. And in a course that has 9 weeks of lectures, if I ended up spending that much time on one particular program, then I don't think I'd end up teaching you the broad skill set that you'll need that you can then apply to these interactive debuggers. So we're going to do things only with the tools that we have at hand, knowing that becoming a good programmer is not about mastering individual tools. It's about becoming a master that can use any tools. So if you wish to own, you must own at all games. That's no one's going to know that one. There's an obscure web series from the early 2000s or something called Pure Ownage. Anyway, so we're going to look at these. We're going to look at using compilers, and we're also going to look at testing today. So if we're going to use our compiler to find the syntax errors, the syntax bugs, the one thing that we can always do is we can trust the compiler, and the simplest thing we can do is just run it and see what happens, right? So at any point when we're writing our code, we can run DCC, and DCC will tell us whether our code is exactly correct C or not. The trick when DCC gives us errors is always scroll to the top and always look at the first error. DCC is working line by line from top down. If it encounters something from the top down that causes an error, that might have a flow-on effect. It might make all the lines after it appear like they're not correct. A bracketing issue can definitely do this. So if you bracket incorrectly sometimes, every single line afterwards will have an error. So you'll have hundreds of errors. So the trick is to take the first error and fix it. And you could nearly, if you wanted to, if you want to boil this down to a process that's easy to follow, I could tell you to ignore every error after the first one, and you'd be fine. Because then you'd recompile, and whichever error floats to the top is the one that you take next. So because errors could be a consequence of the first one, there's no point fixing later ones. In fact, it could cause more problems. So usually what we do, we look at the first error, we fix it, and then we find a way around it. And we won't necessarily know what to do with the first error. But what we will get is the idea that that first error will tell us a line number and a character in the line. So it will actually tell us where something is. And then using that, we'll find out a line that we need to look at. That's not going to solve our problem for us, but it's at least going to say, I've got 1,000 lines of code. and I have one line to look at, and at least that compiler error will give you that one line to look at. And even if I've got 100 errors, I'm still only going to look at the first one. So that narrows down immediately the kind of things we need to look at to figure out why our program's not working. So we can go in and we can go, this line is the problem. Well, it's not the problem. This line is where the consequences of the problem manifested. So sometimes it's easy because the problem is that line, or sometimes that line is where it shows that something above it has caused some problems. So, simple rule. When you compile and you get errors, only look at the first error, use the line number and character to find out where that is. We're going to do a bit of this practically in the second half of the lecture today anyway. I think I've just said this, isn't I? Yes. To solve these, so any errors that are in a compiler, which are usually syntax errors, line number and character. The other thing that we need to do is we need to think about what the error messages are and what they mean. So DCC is a compiler that we've created here at UNSW, and it has much more information than a normal compiler has. If you're interested, you can compile a program that has errors with DCC, and then you could replace the DCC command with GCC, which is the, I think it stands for GNU. GNU is another, it's like one of the Linux systems, C compiler. GCC is a more professional tool, which means it doesn't catch your errors as easily, nor does it give you as much information about what's going wrong. So if you compile the same code in DCC and GCC, you might get a really interesting response. I think one of the worst things that you can get if you compile your code that is riddled with errors with GCC is sometimes it will just compile it. So that's a really scary thing that can happen, is that GCC will just accept your code and you won't know that something's gone wrong until you try to run it, and then it just sort of explodes. Or it breaks something on your computer, or it just casually walks out of the memory that it was supposed to be using and goes off somewhere else into your computer, starts trying to change things, and then, like, I don't know if it'll be that drastic, but potentially your virus antivirus software will instantly quarantine your program for trying to hack the rest of your computer. So I suggest using DCC for now until you get a good idea about the nuance of these things, and then you can use other compilers. There's some inherent danger in using those. But the process is always going to be read the error message and see if you can interpret it. It's not always going to be exact or easy. Sometimes it's super easy. Sometimes it says, I expected this here. And you go, oh yeah, I expected I should have written that there as well. It's like, sometimes I expected a semicolon, that kind of thing. Sometimes DCC is really nice to you and says, are you sure that you want to put a single equals assignment in an if statement? Because I feel like that's not the kind of thing that humans usually do. GCC will never tell you that. GCC will be like, not legal C, let's go, let's start running it. I put a single equals in my PhD code several years ago, and it took me 2 months to figure out that that was a mistake that I'd made. So it's an easy mistake that people can make. This was an AI thing as well, so I thought it was I'd just written bad AI. Not that I'd written code that just literally didn't do what it was supposed to do. Anyway, okay, so the error message, the best way to think about the error message is, this is the point at which the compiler saw something was not working the way it should have. Rather than saying that this is the program can never know the difference between your intentions and what you typed in. It can only know if what you typed in doesn't fit in with the rules that it has, right? So the error message may not make sense when it comes from the compiler, but you will get a feel for interpreting these things the more you use them. So it's really just going to be a matter of looking at that error message and saying, okay, what does it appear to be telling me, and how deep do I need to go into my code to figure out what's happening? Sometimes it doesn't matter if you can't fully understand the error message. Sometimes it's a matter of just going to your code where it says it was an error and trying to get deeper into it and seeing what's happening. Okay, We're about 10 past 10, so it's not a bad time to take a break. I kind of wanted this break slide to be uh, to be after I was talking about testing, but I thought that it'd be funny anyway. So, not knowing um, how your program is going to be used means you can get some really interesting things. So, a QA engineer uh, is someone who's quite valuable in a team. So, this is the person that does a lot of our testing for us to make sure that things are working correctly. The bigger a company you work for, the more specialized roles you might get. So a small startup might not even have QA engineers. Everyone has to do their own QA. QA is short for quality assurance. So we get this hilarious thing. Engineer walks into a bar, a QA engineer, orders a beer, orders 0 beers, orders 99999 beers, orders a lizard, orders -1 beers, orders a blah 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 blah. This is exactly what QA engineers do. They look at all these different possibilities and then they see which ones are going to work and which ones don't. And then what always happens is the first real customer walks in, asks where the bathroom is, and the bar bursts into flames. This is an analogy for what definitely happens with software. We go to all this trouble to try to make sure that we have covered all our possibilities with our testing, but you never know. You really never know until people start using it whether something actually works or not. Which is why I never say that when I release an assignment that it is final and complete and I'm not going to change it. I think we're actually reasonably good at the moment. I know that Tom and Dean have had to make a few little tweaks here and there, but but we even, I think, when was the last time we tweaked the assignment spec? I think it was only a couple of days ago, right? Because we know that if we have 750 people trying to use something, they're going to be better at finding all the issues than we are. And we're not going to find certain issues a lot of the time because we've made assumptions about things. We've already said that we know how this thing works. Because like when we write an assignment, we actually write the solution before we write the questions. So what we do is we code up the solution and say, okay, this was this hard. We know it's this hard because we did it. This is what information we need to give people so that they can try to do this same thing, because we need to take some of the information away so that you can go through the journey of figuring it out for yourself, the problem-solving side, right, which you want to learn. And so our perspective is very skewed on the assignment, which is usually why we have 1 or 2 tutors who are not allowed to know anything about the assignment, and then we throw it at them a few days before release and we say, okay, do the assignment, let us know how it went. And usually that person comes up with a whole bunch of issues with what's in the spec, and we go, oh, we didn't think of any of that stuff. So this kind of thing, real world, definitely happens. Okay, let's take a quick break. I'll be back. What is it now? 10:13. I'll come back around 10:16, 10:17. I'm not sure. 3-4 minute break. I'll come back and we're going to do some actual debugging. Alright, back soon. Hello all. I think chat has devolved again into people trying to order a blah 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 from a bar. Yes. Sometimes it takes a great amount of imagination to figure out how you're going to test a program in order to get the most amount of information out of it. Anyway, let's keep going. We probably will be doing a little bit of testing here. I'm going to show you some of the simplest techniques we use to try to figure out what's going on in a program. But let's have a quick look. Let's look at some code. We're going to fix some bugs. And here's the meme that I was talking about. Is my face... No, my face isn't covering up the meme this time. It's just covering up one of the letters, but I'm sure that'll be fine. This is a classic right here that we find some bugs in our code. We remove like one bug from our code, and all it does is allows our compiler to access more of our code before it gave up. So yeah. Terry, do you recognize this cat? I don't know if this cat, like, this is Grumpy Cat, but I don't know if Grumpy Cat is still that much of a thing anymore. Grumpy Cat actually died a couple of years ago, and that's what this cat's based on. So it's just like one of the cutest cats ever, but sadly has passed away. Yeah. Oh, what a burn! Liang just said boomer memes. Oh my god. I guess I'm old. I mean, like, I've totally gone on boomer memes this lecture because, like, I quoted a movie from 1994 and told you should still watch it. Having said that, I'm going to stick by that. You should still watch it. It's really good. Okay, so let me see. Whoop, nope. I knew that at some point there was a spoiler slide in here that was like, don't look at the next slide. Okay, so let's look at debugthis.c, which is a program that has some bugs in it, and we're going to do a little bit of bug tracking, I guess, and see what we find. So here's one I prepared earlier. Some of the errors in here are going to look really familiar because they are errors that I've seen in students' code before that I've put in here. So what are we on? Lecture 9. Lecture 9, at the end of this lecture, puts us at exactly halfway through the course, actually, because there's 18 lectures total in the course. So lecture 9, I had a demo on using characters. We're not going to look at that yet. I'll look at it later. So I've opened this up. Program is intended for debugging. Doesn't compile first go. Needs a bit of attention. So this is a bit of a reminder there. I think I didn't put my name on this one. That's awkward. Oh well. At least I know what it's supposed to do though. It's intended to loop. Each time it loops, it will draw a square of asterisks that is sized based on user input. So this is similar to a whole lot of lab code. It's similar to one of the examples that I've done in lectures as well, which was like, I think the first time we did double looping. It was just drawing a grid of stars. And we'll look at the code. I mean, it looks pretty well formed. If I was just to gloss over this, I don't think I can see anything in particular that's going wrong or anything like that yet. I mean, like, if you can see it, don't say anything yet, because you kind of know. Like, there is some stuff. Claude, this is not the weekly test. This is a much simpler version. The weekly test is more detailed than this. So that's a spoiler. The weekly test has something to do with two-dimensional looping in it. Although you should probably expect that because it comes the week after learning about some parts of it. Anyway, so let's just see what my compiler thinks about my syntax here. So debug this, output file, just going to call it debug. Oh, there are a lot of problems. There are a lot of problems, more problems. I'm going to scroll up, and I scrolled up to the point where I found the command that I typed in. Usually you can look for this, because the last time that your prompt was there is the last time you typed something in. But I've got this here. It's a warning. Personally, I would never want to submit something as an assignment, and generally I would not want to release something as production code if it had any warnings still in it. Warnings say, so these are the pink ones, warnings. What they say is that we are able to compile this. We're able to read this. It is legal C, but we think that you may have made an error here. For example, you've created a variable and you've never used it. That happens sometimes, and those variables then are basically useless if you've never read them again or you've never modified them. So a warning like that would be to remind you that maybe you wanted to do something else with that. The warning here is the one that I was talking about previously. Exit equals 0 is an issue. This means that in the while loop I'm setting exit to 0. So what I have created here, if I was to run this, is a while loop that will basically never end, because no matter what value exit was, I'm always going to set it to 0, and I'm never going to check whether it's 0 or not, because there's nothing in here that's a question. This is a command that sets exit to 0, and it's always going to succeed because exit's an integer that can be set to 0, which means that this while loop is never going to fail. So this program would never exit this loop. It would stay in it forever. So I think it's pretty obvious that we were asking a question here, not answering it. So I'm going to save that, and I'm going to go back and compile again. So I'm following my own rules. I have literally not read what the next error is. So I'm not even worried about that. What I'm doing is I'm just fixing the first one, and then I'm compiling again. So I'm going to press the up arrow to do my compilation command, do that again. I'm going to scroll up to where I was, and look how few errors I've got this time. It's only one page of errors. So maybe something that I did in correcting that stopped a couple of other errors from happening. Okay, expected parameter declarator. And we've got this. So here is an example of what a normal compiler gives you. DCC is the one we've written that says here's a bunch more information that might be useful. So this is a bridge between you and professional compilers. So a professional compiler just goes blah. But at a student level, what we want to do is give you as much information as possible. So this says if you're trying to call a function, be sure that you're calling inside of curly braces. Yeah, that's fine. Check that the function's header doesn't end in a semicolon. No. Alternatively, if you're trying to declare a function. Okay, that didn't actually help us that much. The DCC explanation said that this kind of error is often to do with functions, and it's potentially to do with functions being used incorrectly. If we look at this closer, debug this, line 47. Here. And so we're looking at this, and we're saying, I don't see a problem here. I don't know about you, but I don't see a problem here. That this printf appears to be well formed. I thought for a moment that the expected parameter declarator might have meant that I had left off an item, but there's no format string in there to link to a variable. So, if you're trying to call a function on line 47 debug 6, be sure that you're calling it inside of curly braces within a function. There's a clue there. Let's have a look at our curly braces and see what lines up to what. Because what if this is accidentally outside of the curly braces I want it to be in? So one of the nice things that gedit does, and most programming editors will do this, is if I click on either side of a bracket, it's going to show me which bracket closes it, which is this one. Very awkward. I would expect the main to close on this bracket, not this one. So if I hover on this one and I go up here, there's nothing else highlighted. So this bracket is just hanging out there on its own, and this bracket here is hooked up to the main, which means I've closed too many brackets somewhere in here. This is a pretty common error. So let's have a look. Opening and then opening the while loop. The while loop is closing in the wrong place as well. So this if statement looks fine. This while loop looks fine. This while loop looks fine. And then we've got, oh, what is that? Wait, that's that while loop? No, that's fine. This. Okay. When we see the two of these vertically aligned like this, at least I did my indenting correctly, so I can see this. And this is really one of those things where if I hadn't been careful with my indenting, 4 spaces in for everything that's inside something else, I would not have seen this issue. And this issue, actually I didn't do my indenting correctly. This shouldn't be indented. There's no reason why this should be indented. So if I bring this back out here, this looks awkward, right? These two closing brackets together where there's nothing in between that opens a bracket, they really shouldn't be on the same line. I think that this is not meant to be here. Not 100% sure, but if I do this, this loop ends here. The main ends after the return 0. That makes more sense to me. Maybe now I won't get the error, this thing saying, are you sure that you're calling this outside of a curly brackets? Because it's no longer outside of a curly brackets. So let's save this, go back, compile it again. Ugh! That compiled. Did it? Let me just make sure of that. We may have gotten rid of all the syntax errors. Oh, actually, we've gotten rid of the syntax errors because it compiles. Whether we've gotten rid of all of the errors, I don't know yet, but at least we know something now. Okay, so what errors did we find? Here's the spoiler slide, in case you didn't do it. We had a single equals if statement, and we had extra bracket causing a lot of issues. Oh, scanf not pointing at a variable. I think I accidentally fixed that before I made it public. There was meant to be a scanf error in here, probably here. Maybe that was missing or something like that. Apologies. There's something in the slides that I didn't actually make into an error in the code itself, but that's okay. All right, people were following along, and they were finding errors there. And Terry's getting fearful that debugging only removes some errors and not all errors, and that's truly the case. There's always going to be some errors somewhere. And as Tom says, Mark is clearly a programming god, can't be any errors now. And Liang wants me to run it to see what happens. We will definitely do that, but let me step through some of this stuff before we do that. Okay, so you can see how the extra bracket caused a whole lot of errors, but we didn't have to look at them, so I ignored them completely. There were several errors after the one that I fixed, but I didn't look at it, because sometimes it's more important to not look at it. I'm just gonna remove that because we don't need that. Okay, so we're still not sure if it works. So the simplest thing is, let's run the code and see if it works. And if it works, we can try different inputs to see what happens, because sometimes we want to figure out whether we're working for all possible cases. Note that when we use autotest doesn't exist out in the wild. It only exists in certain subjects within CSE. Autotest is us writing possible test case inputs for you. So this is what autotest is. It's us saying, okay, what are the possible things that we want our lab exercises to be able to do? And so we test you on those. In the real world, you write your own. So we're going to look at testing some of these ourselves. So there's a couple of things that we can do to figure out what's going on. We can use output partway through the program. This is output that we're never intending for the actual performance of the program, but we can actually use stuff like printf statements to tell us what the program's doing at a certain point. It's a pretty unsubtle way of doing testing. There are more elegant ways to do it as you get further on, but what I want to get us into the mindset of is that if we can understand what our code is doing, it's much easier for us to be able to figure out where and when it's going wrong. So let's do some testing. Let's are we? Yeah, okay. I was going to go through a little bit more before I actually go into that testing. So we can write our program in a different way so that it gives us extra information. And usually what we try to do with testing is we say, let's test with a specific idea in mind. Let's test if something does or doesn't work with certain things. So what we're trying to do, and this is the professional skill of a QA engineer, because as it gets more complex, it's much harder to do. How do we break the program in very specific ways? How do we break the program so that only one type of error comes out of it? So for something like freefall, I've used this example several times when talking about freefall. You've got a square grid, and you've got 4 boundaries that you could exit at any particular time to cause a problem, like an array out of bounds error or something like that. What we can do is we can take a single step outside each boundary. So we don't go too far outside the boundary, we just take a single step outside each boundary and we check if all of those are correct. We don't do diagonals yet. I mean, we could do diagonals, we could check 8 boundaries if we wanted to. And what we would do is take a single step outside each one to say, are we detecting those boundaries correctly? You know? Because I think there's a couple of places in freefall that says if something tries to be outside of, so if someone tries to create a line of stones that is outside the boundary, then the entire line shouldn't draw. So we need to be able to check for those things, right? And so when we test, we want to test all of those things to see whether they work or not. And then the thing that we do here, and this is this bold bit at the bottom here, you're looking for a needle in a haystack, right? You may be looking for a single character that's off out of thousands. But the smaller your haystack is that you're particularly looking at, if you split it up, one haystack into 10, and you know that it's in one of those 10, it's much easier to find it. So what we do is we actually separate our code into bits that we know are working and bits that we know aren't working. And this is one of the reasons also why we have functions. If my code is separated into a series of different functions, I can test each of those functions on its own. So I can test one function and say, do you work? I can test the inputs and outputs just to that function. Sometimes we get really, really drastic and we can copy that function out of our program because a function works on its own. It doesn't need anything else in the program to work. So I can take that function, put it in a new file on its own and run testing on it. And when I've run that testing on it, I can say, all right, this function works. It can go back into the program. And if I do that with all the functions, I should be able to figure out which one of them isn't working. But we'll see how we go. All right, so seeing which bits of the code work and which bits don't is pretty handy because then we can sort of narrow down. It sort of narrows our focus on what we're looking at. Okay, so let's continue with our debug this, and we can look at how it's meant to run and how it runs. Test some different inputs, and also I'm going to do some modifications of the code which aren't going to lead it towards functioning correctly, but instead this is going to lead us towards knowing more about what it does. So here we go. We've compiled it. It has run. Sorry, it hasn't run yet. It's compiled. Let's run it, see what happens. Please enter the size of grid you would like me to make. If you would like to exit, please type 0. Let's start with 5, see how we go. Now, I'm not getting lag issues at the moment. I know, because I've been using VLab a bit in this lecture and I wasn't getting any lag issues, so I'm thinking something's wrong here. I know that the program is not terminating, it's not finishing because I don't have a prompt. My guess is that there's a loop here that isn't finishing. So there's a loop that's going forever. My processor is just spinning at 100 miles an hour, just doing this loop over and over and over and over again. So I'm going to try to exit this now and see what information I can get out of it. So Control C, I'm going to type in Control C here into my terminal, which is going to stop my program. Okay, execution was interrupted, was stopped in main in debug this at line 29. So here's a loop at line 29, and I guess that this loop isn't finishing. Now, when I go in and look at this code, it might be obvious to you while this loop isn't finishing. But what I don't want to teach you how to just look at the code and go, oh, I can see what's wrong. What I want to teach you here is how to figure out how a loop is or isn't working, regardless of if you know the answer. You know, so there's no point in me teaching you, oh, always put your I++ in there. There's probably going to be an I++ or something. But what I want to teach you is when you can't figure it out that easily, what's the process we're going to go through to try to figure this out. So we're not even at a point where we can test the different sizes. We've got something that's just literally not working. So this is our most basic logical error. It's just stopping it from working. So line 29, it's this one here. So we can kind of, if we just eyeball this, we can see that y is not being incremented. But what I want to do is I want to show you how you could find out this information even if you couldn't see where the issue was. So what if this while loop is a much bigger, like it's like 30, 40 lines of code, and there's all this stuff going on, and you think the incrementing is working correctly, and you say, okay, I need to figure out what's going on. So what I will usually do is I will tell myself when this is running what's happening. So the simplest way is I can put some printf statements here, and I can say entering loop it's actually entering the double. All right, I'm going to say entering outer loop. I'm just going to call it entering outer loop here, and then I'm going to say in here started loop number this, where the number is y, so I know which value of y. Actually, you know what, I'm gonna make this explicit. Y is equal to this, and I've got this inner loop here that I want to look at as well, and I'm gonna say printf started inner loop. Oops. I think that's the funniest thing is, like, what if I was adding code so that I can debug things and then the code itself has syntax errors in it? I think that would always be really funny. X is equal to something, and I'll put a new line on that, and this is X. Maybe that's enough for now. Actually, I could put more info in here. Printf finished in a loop, and here printf finished outer loop. So what I'm doing is I'm saying there's something wrong with this loop. What I want to know is what's going on. So now I have a whole bunch of information for what's going on. So when this thing runs now, I should be able to see what's happening. I should be able to get some information about what's happening here. So let's run this again. And depending on what print statements come out, which of these get printed, I'll see where I get up to, and I'll see some information about the Y and the X in here. Note that if you're looking at this carefully, you can already see. So this is like when I was talking before about like the style thing. I think it was like, he's behind you. Some of you will see what's going on here, but some of you may not and this may help you learn to do that. It doesn't really matter whether you can see the solution or not here. What's more important is the process that we can follow to always find a solution to different issues. So, let us compile this again and run it. For the moment, we're just going to stick with the same grid size because I don't think the grid size is important. If I've got an infinite loop, then I've got bigger problems than the size of the grid. Okay. So Control C on that because I am getting all the information I need here. I'm getting a lot of information here that's quite useful. So, started loop y equals 0, finished outer loop, started loop y equal, finished outer loop. This is just going over and over and over again. So I know the thing that's going on forever is this. Started loop here, finished loop here. So I know that this thing's going forever. When a loop is going forever, that's reasonably easy because one of the things I taught you about loops is every time we create a loop we want to know how it's going to finish, and so we can see that y less than grid size, so this is what people were saying. I'm assuming that this should be going like this. The other piece of information we figured out here, started outer loop, finished outer loop, started inner loop is never running. So there's something interesting there, that x less than or equal to grid size, x is not less than or equal to grid size. Do we have a x is equal to 6? Slightly more subtle for what's going on here is that each time we were using x was too high to be used inside the grid. So there's something going on here, and this is actually a reason why I might not want these variables to be declared at the start of my program like this. There's a sort of a rule of thumb that people do with variables sometimes, is that they declare the variable as late as possible to be able to use it. So I'm going to take my int equals y here, and I'm going to put it just before this while loop, and I'm going to take my int equals x, int x equals 0 here, and I'm going to put it in here just before this while loop. Now note, I was just moving some lines around, but it's very, very important what happens to these, because every time the while loop runs, x gets reset to 0. The reason why x was failing this less than grid size check is I was adding it up until it got beyond the grid size. This is the first time it loops. And then every time afterwards, x was already equal to 6 because I hadn't reset it. This is actually one of the unwanted side effects of me declaring my integers at the very beginning like that, which is a slightly dangerous thing to do. Instead, if I declare it just before I use it, then this entire loop will work in here like this. So I think now the while loop will work and the x loop will work. But let's save this and run this and have another look. Sorry, compile this. Oops. Use of undeclared identifier x on line 43. Ah, interesting. I was resetting x to 0 so that it could print the next line. That should have been inside those brackets. It actually looks like, you know how I had the two different possible closing brackets? I think the issue had always been that. The closing brackets should have been outside there, and then this idea of printf of a new line ending each row makes sense because it's inside the row loop. Resetting x to 0 would work now and I wouldn't need that, but I mean I don't need this at all now because I'm resetting x to 0 before I start each time. That doesn't look right. I changed that to y++. Oh, if I leave this in here, that could cause some really, really weird issues. So let's get rid of that as well, because that doesn't look right either. So you can see there's actually different ways I could have solved this. If I had changed the location of those brackets first, I would have come about this problem a different way. That y++ would have been solved if I hadn't solved the bracket issue the other way. So think about this carefully. I solved a syntax error, and in solving a syntax error, I caused a massive chunk of logical errors. And either way that I'd done that, where I'd put that bracket, it would have caused different logical errors, right? So there's a whole lot of interesting stuff like this that causes a lot of these issues. There's also some weird stuff going on. There's inconsistency here in my iterators. This is y less than grid size, and this is x less than equal to grid size. So once we start testing this, we could see some other issues. But I need to compile this again. Line 46. I'm resetting variables for my next run through. Since they're getting reset when they get created, that's probably okay. So there's lots of fiddly stuff in here where I think when I created this the first time, I was answering the question a different way than the way I'm thinking right now. So let's see if we're actually... Okay, we're compiling. Let's run this and see what it does now. This is looking much better. So there's all those stars, but we've put all this text in between them to see what's going on, but at least we can see what's happening. So starts the outer loop at y = 0, counts x through to 5, finishes the inner loop each time, finishes the outer loop. The outer loop then increments. It's going all the way up till y = 4. So I think that this is functioning similarly to how I want it to. I'll just put a 0 in there so I can exit. Okay, the exit's working. This one says have a nice day, isn't that nice? So what I might want to do now, for the moment, I'm going to comment out these debugging statements and see whether this functions correctly or not. Compile this, debug, 5, okay, sort of okay. Subtle issue here, which people may have already seen. I've got 5 rows, but I've got 6 stars in each row. So if I've got 6 stars in each row, then I'm going to look at the loop that does each row and see where the issue is, and I think I've already pointed this out. I saw there was an issue here. So if we save this and compile this again, we should get a the correct functioning of this program. There we go. 5 rows of 5. When I'm happy with this, I usually want to get rid of these, because I only needed these to solve the problem, and I don't want them in there because, as you can see now, it looks like there's a whole bunch of comments in here. Someone's going to try to read these, and if they try to read these, they might miss the important comments that actually say what's going on. So now that I think my problem is solved, I'm going to get rid of all of this diagnostic stuff that I used to solve the problem. And now I've got a better idea of what's going on. So that's just one of the things that we can do. So I wanted to talk about what we did. We can try different input. I didn't even try the different input ranges, right? So there was different tests we could do. We could have tried negative numbers there and seen what happened. Actually, let's quickly do that. -1. Not too bad. This is going to go bad. It wasn't that bad. It was able to kind of deal with that and just go, nope, we're going away. We're going to do this as if you typed the 0. So there must have been something I did right there. Scanf, grid size. I think I got lucky there, because grid size appeared to just reject this and exit. I'm not sure why that exited properly. Anyway, we got away with that one. Alright, so we had different possible testing. We also tried seeing what our X and Y values were to make sure they're working. We also outputted loop information to see where we were, and so we saw which parts were working, which parts weren't. So this kind of thing is what you can do to get closer to your program. So you can see how it's running and you get more information. So if the code is syntactically correct, that doesn't necessarily mean that the code's going to work. But when it's syntactically correct, we can start running these kinds of tests, and we can start putting output statements in there, and we can start trying different input ranges and stuff like that to see whether our code is doing everything that we need it to do. So lots of little tricks like that if you use this kind of process every time you're not sure whether your program's doing what it's supposed to do or not, you should get more information. It's never this is never like the only solution, but what I'm trying to do is give you some tools to take that big haystack, your entire code file, trying to find the issue, and shrink it down so you can see which bits are working, which bits aren't. So we can see which parts of our loop are functioning correctly, which parts of our loop are going forever, which parts of our loop are running just a little bit too long, like the grid size and stuff like that, like the x greater than or equal to grid size. So all of those little things will allow you to see exactly what's going on. Okay, I've spent a little bit too much time on debugging, but having said that, I said we're going to spend 80% of our time on debugging, and we spent 80% of this lecture on debugging as well. Dean's answering some questions there. It's like everyone was like, six, you did it 6 times. That's pretty funny. Okay, so let's talk about characters. I've got a little bit of time left to introduce characters. Don't worry about whether I get through all these slides or not, because next lecture we're going to be using characters again. So if I don't finish this today, that's fine. We'll talk about it on Thursday. So I'm introducing a new character type. New character type. Too much debugging. My brain is fried. A new variable type called char, which is short for character. Characters are what we think of as letters, like ABC and stuff, but they're not just letters. We can also see that the numbers are characters. If you look at your keyboard, I'm reaching out and touching my keyboard now. That's not helping you because you can't even see it on my camera. Pretty much, it's not exact, but pretty much every key on the keyboard is a character. In C, we're actually using 8-bit integers to work as characters. So 8 bits, there's 256 possibilities, and there's 256 is way more than the number of keys we have on our keyboard. But it allows us to represent everything that the keyboard can do and some other stuff as well. So these 8-bit integers that are our characters are actually just numbers that correspond to letters, in a sense. It's not just letters. I'm going to say letters because it makes it easier for me to say it. Yeah, so each one corresponds to something, and that's using this thing called ASCII. Now, we're not going to go deep into ASCII because ASCII is not necessary, but I want to talk about it because it gives you the idea about the fact that the numbers and letters are actually interchangeable. So one interesting thing about the character variable type is we're actually often going to be using integers to represent characters, and there's subtle reasons for why we're going to do that. So ASCII is actually slightly less than 8 bits there. I think that's 7 bits, but it uses the 8th bit for other things. Specifically, the value is 0 to 127. You can look up an ASCII table online if you want. It'll show you what the actual numbers are. So, for example, I think the lowercase a is 67 or 97. I don't memorize this. I don't want to memorize it because it's just a table of letters and numbers, right? So we're not going to be using ASCII, but I want you to think of letters as numbers because they are interchangeably letters and numbers. So that's why I wanted to talk a little bit about what ASCII is. So this gives us all upper and lowercase English letters, so ABC through to Z. It gives us the digits 0 through to 9. It gives us the punctuation symbols, but it also has some cool invisible characters. So space and new line are also characters. And we know this because we've been using them. Like, we've actually used new line a lot in our printf statement. So we know that it's something that can be sent to the terminal, that kind of thing. And what I'm talking about now is that everything that we've been sending to the terminal has been a character. So it has been something that can be represented with this numbering system. So as I say here, don't need to memorize ASCII, don't even need to know. But it is useful to know that letters and numbers are actually interchangeable. So every letter has a number code attached to it, which means that you can, if you really want to, you can do arithmetic on numbers. So if I do A plus 1, I'm going to get B. Don't trust that. Don't trust that all the time, because the ASCII table may put all the letters in order, but once you go off the end, you might have other issues, right? So when we're using a character, I can use an integer to represent a single character. So I have here int character. Because the character is a number, I don't actually have to use the char variable, and I'm going to show you why later on, why we wouldn't necessarily use the char variable. So int character, and I can assign a character now, and so this is a new thing, single quotes. We've been using our double quotes here for groups of characters together. If we want a single character, we do use the single quotes. The single quotes is actually going to store a number value here, which is why this is okay with an integer. So this is exactly the same as me putting like number 5 or something. But if I do the single quotes, it says, all right, you want this letter, and you want this letter to be stored, and so it will use the ASCII value of that letter. Don't worry too much about what the ASCII value is. You can see that I'm not even using the actual ASCII value. I don't need to look it up at all. I'm just saying that I can store a character in an integer. And if I want to, I can print that out, and this will say what the ASCII value is by looking at the same variable. You can look at it like it's a character, and it will go, okay, what letter are you that's encoded? Or if you look at it like an integer, it will go, okay, what was the code that you had? So they're kind of interchangeable like that. I actually have a demo here. That has the code from the slides in it. So what I'll do, just going to comment out the bits of it that I'm not going to show you yet, and I'll show you the code from that slide running. Okay, so this is the code from that slide that says the letter A has an ASCII value 97. Oh, so it was 97. Did I say it was 67? I think I wasn't sure which one. I forget, doesn't matter. So this is showing that if I set something up with the letter A, it also has a number value that can be used. Generally, we're not going to use the number value that much. We're just going to use letters like this. So I could say, is this character equal to A? I could just say single quotes A rather than ever using 97. I don't really want magic numbers in my code. I would much prefer to have letters like this that I can understand. Okay. Oh, the printf %c allows me to print one single character like that as a character variable. There's a lot of cool functions that we can use. Tom and the others are using what's known as ASCII art, using characters to do art, but I think some of those are not actually ASCII. They might be an expansion on it. We're going to be using pretty simple stuff. So there are a bunch of functions that are in the standard input-output library that are really useful. I'm going to have to wrap this up pretty soon. GetChar is one of these. GetChar just says, I'm going to take exactly 1 byte of standard input. So remember, a byte is 8 bits, and I just said a char is 8 bits. So if I grab a byte, I'm grabbing a character. They're exactly the same in terms of size. They're not the same. Like, a byte is a piece of memory that's 8 bits. A character is 8 bits worth of information. So getChar can return an integer between 0 and 255, which is the ASCII code of what byte it read. So this is like me doing scanf, but me not saying that the scanf has to match a particular format string. So I'm not saying this has to be a floating point number, or this has to be an integer, or something like that. What I'm saying is I don't care what it is that someone's typed in. I'm going to take the individual characters that someone has typed in, and then I can use them however I want. The getChar will always return between 0 and 255, but it could return the fact that we didn't get anything. So end of file, which was seen before, it can return end of file. getChar can say -1 end of file, that's a hash define, and it will say at this point I did not receive any input, so I've reached the end of the input. And we can simulate that with a control D when we're doing things like reading files, which we're not doing in this course, but you will learn later. When we're reading all the text out of a file, which is really similar to reading the text in a terminal, we would reach the end of file at the end. So this will return a -1 when it reaches the end of the input, and this is why we're using integers. We use integers rather than characters, because if we get a -1 and we use characters are only between 0 and 255. So characters don't have negative numbers, so we would never be able to tell if we got this negative input or not, which is why we use integers a lot of the time. So the integer says I can not only store 0 to 255, but if you give me a -1, I'm going to know about it as well. The other thing about getChar is it's not going to get every single character the second you type in. As you type stuff in, it doesn't go to the computer yet. It's just sitting in the terminal waiting until you press enter, and then all the characters will go in at once. So if you're looping with getChar, it still may not run the first bit of the loop. Even if letters have been typed in, it may not run it at all until the enter has been pressed and all the characters get sent in. Putchar is really similar, where what it will do is it will print a single character to the screen. So this is nearly exactly the same as if I did this printf and I grabbed a single character and did this. So we've got some code here for getChar and putchar, and I'll show you how that works. Here. So I might just comment out this first bit because I don't think we need this. So this is the code from the slides there. It's got an int and it reads that in using getChar and then tells you what it is, but then also puts that character out afterwards. So let's compile and run this, and I'll show you a quick demo of that. And I think that'll be it for today because I'm a bit over time. Okay, enter a character, character U. U has the ASCII value 117, so it just happens to have a number value, and it's there. Show you this again, something interesting. So I'm going to put in the character 9, and the character 9 has the ASCII value 57. So the interesting thing is the character for the number 9 does not have the number code for 9. So just be careful when we're translating between characters and numbers that we can't just use a character as a number. Or another thing that we could do here, please enter a character. I'm going to put the space bar in there. The input space has the ASCII value 32. So even the space bar has a number code because it is a key and it is a character, because a space is a valid character. So some of the invisible characters also have values. I wonder if we can, I'm just going to press enter. Yes, that works as well. So the new line that we've been using the /n as, the new line character has an ASCII value as well, ASCII value 10. So this is a way for us to be able to say all of the characters that are potential to be output and things like that, they all have codes that we can use. I'm going to leave it at that. I had more stuff to talk about with characters, but what we're going to be doing is using those on Thursday. So I'm going to put the rest of the slides and characters on Thursday, and we'll go back over this again. Okay, Patrick is saying getchar and putchar, are they from standard input output? Yes, they are. So if you look here, the only library that I used was standard input output. And you can tell that they're kind of, you expect them to be standard input and output because they're talking between the program and the terminal. Lang's asking why we don't align 0 to 9 to 0 to 9 ASCII. The reason I think is that 0 to 9 ASCII are for special codes, and so there's all these special codes that come at the beginning. So you see how new line is number 10 and stuff like that. So there's a bunch of special stuff that happens at the beginning and then it goes on to the actual characters. So I think that this is not necessarily about making them line up to make it easier to use. This is a legacy of the fact that this was encoding for how a keyboard was going to send signals to a computer back in the day. So I don't think there's a particularly good reason why they don't line up. It's more of just this is how it's ended up, and we just have to be careful never to use the characters for arithmetic if we're expecting them to be numbers. Okay, sorry, I've run over time. What I'm going to do is I will wrap up the actual lecture here, but I'll stick around as usual for questions afterwards. So I'll take a quick break. So if anyone needs to go off to your tutorial, I apologize that I've made you late for your first tutorial for today. But I will just do a quick break here, and I'll come back and I'll answer any questions anyone has. All right, I'm back. I did see a few questions there. So where are we? So I was talking to Liang before about the 0 to 9, and I think Tom had a lot more information on that. And so Tom says take that to the forums because he wants to answer that question, which is totally fine. I think there's a lot more details going on there. Priya's asking why would we use getchar in a printf statement instead of %c. I think you mean a scanf there. So when I say, oh sorry, putchar. Oh, putchar and getchar. I mean, I get what you're saying. It's like why would you use that instead of just something like this? Putchar and printf are, if you do it like this, they're the same. They're pretty much exactly the same. The difference, I guess, would be that I'm pretty sure this is a legacy thing where it used to be that putchar was the only thing that existed, and then people were saying, we kind of want to be able to print lines of characters, and so that's why this ended up being created that could do more than one thing. I think that the only reason, like getchar, I can definitely see using getchar over scanf, because scanf says I'm going to take a single object, and that single object can be formatted into something. So, for example, if I say scanf an integer, it's going to take a multi-digit integer and still be able to do it. But if I'm trying to read specific letters at a time, so what if I don't want to read the whole integer, but I only want to read the first 3 digits of something, then I would use something like getchar for that, because scanf can't really do that. Actually, I guess you're right in saying that if I did scanf with the %c, then I would be getting a single character at a time. So yes, it is a little bit redundant that they would be doing pretty much exactly the same thing. And scanf can still test to see whether it's picked up a character or not. So there's not a huge reason specifically to do it. We could potentially, if we wanted to, only use printf and scanf for single characters and things. I think that would do a similar thing. So I think the only thing that we'd get that would make it easier is that these are just a bit quicker, the putchar and getchar. Finn's asking, how does getchar return a value up to 255 if ASCII only goes up to 127? It's a good question. What are we looking at? Getchar. Oh, there's actually even... Did you see that the autocomplete? Getchar versus scanf. So that's actually really interesting that other people have asked the same question you're asking, Priya. And there may be more information about that. So this is saying, yes, it returns the character read as an unsigned char cast to an int. That means that we're getting the character value as an integer, or end of file on end of file or error. It's not giving us much information about what the difference is between the 127 values of ASCII. I'm just going to look up the ASCII table here so you can see it. Here's an example of an ASCII table going from 0 to 127. Also, Liang, this may answer a bit of your questions about the 0 to 9 because they're very specific. Right. Everything that we've got at the beginning here is commands for things. So there's null, so we actually do have the option for null as a character. Start of heading, start of text, end of transmission, inquiry, acknowledge. There's a bell. So I think there's a lot of stuff left over from an earlier era of this stuff here, which is quite interesting to look at, actually. The bell would have been equivalent of a typewriter, and I'm wondering, I don't know if this is necessarily the case. I think Tom wanted to answer this, so he has some more trivia here. I have a feeling that these codes might actually correspond to the keys on an electric typewriter, because there's a carriage return and there's shift turning on and off and things like that. Vertical tab, line feed, new line. There's all this other stuff. Oh wait, line feed, new line? No, there's new... Oh yeah, NL line feed, new line. That's the one we know, new line. So there's all this interesting stuff here that we don't necessarily use in modern computers, but still exists in the ASCII code because it was created so long ago. I have a feeling that us using the 0 to 255 is probably based on the fact that memory comes in chunks, and so we would never really have a 7-bit value, which is what the ASCII is originally. So I think the 8th bit was for something else. I don't even know personally what it is. But the smallest chunk of memory we would ever use is 8 bits anyway, so we're going to use 8 bits for those characters, even if the ASCII value is not going to make it all the way up to 255. James is asking, what happens if you put in 2 letters, such as AB? So getChar is only going to take 1 letter at a time. If you put AB, it's going to look at the first letter. If you want to, this is the thing that I was going to show you afterwards, which I'll do again on Thursday, because most people would have left by now. If we loop through doing multiple getChars, so that here's a getChar at the end of the loop and a getChar before the loop starts, and it's just going to run if it's not end of file, then we could type multiple characters in, and it would check all of those characters and say what they are. I'll show it to you now. But bear in mind, I'm going to go through and do this again on Thursday. But I'll show you the multiple characters thing. Going to compile that. Run it. Type in multiple characters ending with Control-D to stop. So you said AB. I'm going to go A, B, C, D, D, E, F, a couple of spaces, and an enter. And I can keep going. And just Control-D. And we're going to look through this, and it's like, okay, if we were to loop getChar, then we can get multiple characters. And note, I think that was important, you see how this ran. It waits while I'm typing these things in, and it doesn't send the characters to the program itself until I press enter. Then when I press enter, all of this comes out, and I press enter multiple times here. Oh, no, these were the spaces. I put spaces there, so the space is code 32. And then when I press enter, it prints all of this out. And then I typed in another set, and here's the ASCII values, etc. So getChar is going to grab its stuff once the text gets sent to the program, and if we loop it, we can definitely do multiple getChars in a row. So this is the way, if I was really careful about what someone is typing in, and I wanted to know absolutely everything someone was typing in, I could do that with getChar. Note that scanf is going to ignore all the white space, so I would never be able to read the character 10 or the character 32 with scanf. They won't be read because they're spaces. They're considered not text to scanf, whereas getChar is going to say no, all of this is character input. So I guess that is a decent answer to, now that I'm thinking about it, to Priya's question earlier about why we would use the difference between scanf and getChar. SK is asking a style question here. Is it a bad thing to have too much white space in your code? Yes, but to a certain extent. It's a bad thing to have this, for example. I mean, sure, you're making it really obvious that these are different sections, but you didn't need to make it that obvious, right? That's an extreme example. If I had 2 lines here, let me just do this. That's not that bad. That's me emphasizing that this is a different section to this. So I could do that if I want to. I have seen other people do this. Oops. When they're wanting to separate sections, that's totally fine. Did we do that in the assignment? I don't think we did that. Between the stages in the assignment, but sometimes, I think that might be the second assignment where we have ways to separate the stages. So sometimes people do this, or even they can go, oops, I just wanted to select some of this. Do this as a heading. So this is looping. This is, let me just copy paste that. And this is like single character. I'm gonna need to get rid of some of these. Some people do this kind of thing to show that we've got different sections. So you can use a lot of white space to separate things. You can use giant comment headers like that if you want to separate things. It's up to you. But I would say that, like, once you get to like 4 or 5 lines, then you're just wasting space, and there's not really, you're not going to get more out of this than you were going to get with just like a 2-line gap is already visible enough that you can see. The 1-line gaps I tend to use, and you can see it pretty obviously, like here's a section that does something, and then we're starting a new idea here. We're setting up its own variable and we're doing something else. So that gets its own section. There's a difference between the reading the input and then writing something else out here. Whether or not I needed this space here, I'm not sure. Like, I could have put these together, I guess. And there's going to be a space here before we start the looping thing. Right, that's helpful. I have no problem with that. If you want to use more to categorize things in different ways, you can, but don't go too far with it, right? I don't think you need more than that. So, other questions? Yeah, Tom's confirming that there is a bit that is built to work with a typewriter. And Michael's asking if we would loop through and put characters into an array. You could definitely do that. So we're definitely going to start working with arrays of characters that we call strings, and we could definitely loop through and take all of our input and put it into a string. Claude's asking for a clarification about what I was saying about get the first 3 characters. So let's show this. I'm going to get this looping thing here again. So if I'm going to loop and read characters, let me just compile this and run it again. So let me just do 1, 2, 3, 4 and Control D. This is going to read in the character for 1, the character for 2, the character for 3, the character for 4. That's interesting that I do Control D and this doesn't finish. I wonder what it's doing. Oh no, it's still looping. Right. So the Control D didn't exit that loop. It's a bit weird. Anyway, so scanf, if I was to type in 1, 2, 3, 4, like so, scanf would consider them to be a single object with the with %d, and it would read all 4 of them. But if I wanted only the first 2 digits for that, I could say, well, I took the first 2 characters and I put them in an array, and I could take some of them without needing to take the others. Whereas scanf is going to convert, well, if I use %d with scanf, it's going to convert them all into a single number. If I wanted to, I guess I could use %c with the scanf, and I could read in the, I think I could read in the individual characters. So again, I think it's coming back to the idea that they're functionally what they're capable of doing. Scanf and getchar can do the same things. That, as Tom's saying there, that there is a slight difference in that getchar and putchar are more specific program calls that really just do the bare bones of just getting the character, whereas scanf and printf have got a bit more overhead of other things that they do. You don't really have to worry about that though. That's just if you're looking for like absolute efficiency and things. Okay, so James is asking about AB. I think we've covered that. Like if we type in more than one thing, we would need to loop it to be able to use it. And Tom's saying that Jashank, who's one of the other subject admins, has a printer that uses the typewriter stuff. That's pretty funny. We used to have those printers that, you know, nowadays printers just print like ink on paper. We used to have printers that literally had typewriter wheels inside them, wheels of letters inside them, and so they would actually hit the letters onto the paper through a belt of ink. like the same way a typewriter does, only it was a computer printer, so it would be like the only things that it could print are characters, so it could print all of the different ASCII codes basically. So the ASCII codes would go to the printer, and the printer would print out a document. And so that's why they have those printer fonts, because it's like the same, well, not printer fonts, but like the fonts that are the typewriter shape. We used to be able to print those as well, which is kind of funny. And I love that Jashanka's got one of those. Oh, okay, some details here. Tom's saying that above 128 you could use other things. So there's plenty of other languages that have different letters from English, and they may use different ASCII codes. Yuji is asking if Enter's ASCII code is not printed. Generally, Enter's ASCII code is printed. Here, you could see that the Enter, while it's being invisible here, so it is actually being printed when it says, in a sense, the Enter is being printed, the new line is being sent to the terminal, which is why this one ends up on a new line. But the ASCII code there is 10, so we are still seeing the ASCII code for Enter, but Enter is actually just splitting our output onto lines like this. So this is like one loop through where it does the printf. Here's another one, but when it prints out the letter /n, the new line, it will just split these lines like that. Finn's asking how I get the cool colors in my terminal. The command, I think, is 1511 colors. If you're using the same terminal in VLab, then we are. So what I would do then is, after running 1511 colors, I can close my terminal and reopen it, and then I will be able to have these colors. So that should be fine if you're using the same terminal that we are, if you're using the default stuff that we are, Finn. Tom's saying white space is like water. None is deadly. Some is great, but different people like different amounts. Too much and you drown. That's such a good analogy. I really like that one, Tom. Charles is saying, are we allowed to have comments cross the 80-line character width? No. Don't bother. Because if you do have comments cross the 80-line character width, like, because comments can be formatted any way we want, so there was never any need to have them go over 80 characters, so just use your vertical space. We're going to be applying the same style rules to comments as we do to code. So note that when I have, this is a really bad example because I have so few brackets, this one will have a better example. If comments are inside a body of code, they're indented to the same level, because otherwise we confuse people. So if I did all my comments like this, you can already see this is horrendous, right? I can already hear people going, no, stop doing that, that's horrible, right? This is why the comments will follow the same rules as the code, because then they keep the shape of the code nice. Okay, Gina's asking, this is unrelated to what's being discussed right now, that's okay, but I'm getting an error message, invalid operands to binary expression int pointer and int. I don't understand what that means. I think Tom's answering that already. Binary expression is something that takes two things like a plus b, and it's saying that, I think that's saying that you're giving a pointer and an integer to something like an addition or a multiplication, and it's saying, like, I really don't do that. I don't multiply pointers and numbers because that's weird. So it's probably something like that. Yeah, and Tom's explaining that there. So Catherine's asking, can you collect a 9 in char and then change it to an int so you could use it in a calculation? Yes, you can. Scanf is easier, but you can convert them. I haven't told you about that yet, but there's actually a library function that does it. There's actually, the downside to this is there's like 3 or 4 library functions that do it. So we're going to pick one of them later on, and I'll show you how to convert that ASCII for a number. So character 1 with ASCII code 49 can be converted back into a number, but We'll talk about that later. I've barely introduced the characters yet, but we'll talk about how to do that. I think actually on Thursday we'll probably already start talking about reading numbers in. We'll see. I haven't gone back over those slides recently to see. Gina's looking for more clarification there. You haven't created a pointer, so you're confused. The thing that you might have there, even if you don't have a pointer, is you might have an array. So you might be multiplying an array by accident, because arrays are going to look like pointers to the program. So it could be an array rather than a pointer that the issue is there. So Claude's saying, cool, so scanf takes everything between two white spaces as one unit, and looping getchar takes one character as one unit. I think so. One thing that I haven't tested, because I would very rarely do this, it's always a great thing when I get questions from students, because I haven't tested if scanf with %c is going to take only a single character and is going to differentiate between characters and numbers or not. So let's try something. Okay. Just coding on the fly here. %c, so the character goes into read char, and then the result of the scanf goes into result, and while result is equal to 1, so I did read a character in, then I say I read this character with this ASCII code. So read char should still be that character, but instead we're doing this result thing there, and then we'll take this and put this here. So what I've done is I've just converted that bit of stuff from using getchar to using scanf single character instead. I think I've done the correct code here. Let's compile it and see if that likes it. And run it. Okay, multiple characters, blah. Still works. Okay, so using %c with scanf is separating characters. Let's see if it's separating numbers. It is still separating numbers. So I think what we can see here is that getchar and putchar and scanf and printf with a single character are functionally identical. We could use them for exactly the same things if we want to. So what you're saying there, Claude, that only makes sense if I was to change this to another format pattern. So if I use %d here, then it's going to specifically look for numbers. It's only going to accept numbers, and it's going to separate the numbers with spaces. But %c is able to deal with individual characters one at a time, and it's functionally identical to getchar. It's not exactly identical because the output is different, so I'm still using the result of how many things it read in to say whether I'm going to continue looping or not. So Yuji's asking, why does the code wait for the getchar to scan in characters and then print the result afterwards, though the getchar is assigned to read char at the end of the loop? So what we're thinking about here is, I think, the order of things. You know what, I'm going to Control Z and get us back to the code that we were doing before. Remove that experiment that I've just created. Okay, I think that's it. That's where I was. So we've got the character that's being read in. We read it in once, and then if it wasn't end of file, we print it out, and then we read another one in. So nearly this could be considered to start the next loop. So we read another character in, If it's not end of file, then we print it out. So, e.g., I'm not sure if that's giving you some more information on exactly how this is working. So we read it in the first time so that we can test whether we actually got valid input the first time before we start printing something out. And you're saying, why does the code wait for the getChar to scan in characters and then print the result afterwards? I'm not sure if I get exactly what you're asking there, but I think you may be thinking about this here, where it takes multiple characters before we press enter. This is because as I'm typing, none of this stuff goes to the program yet. It's still in my terminal, and I can still edit it, but only when I press enter does this definitely go into the program. So you can see all those backspaces that I had, they never went to the program. So I don't know if that's what you're asking about. And Weiwei's asking for the difference between... okay, good, great, EG. Weiwei was asking for the difference between scanf and getChar. I think I may have shown that now, that if it comes down to it, there isn't a difference between scanf and getChar. So I think that demo that I showed there actually showed that if you were to scanf with %c, or printf with %c, you're going to get the same functionality as getChar and putChar. Alright. That's working for you now, Gina? Okay, that's good. So I think it may have been the array is a... It's like an array is a pointer, in a sense. So the program is seeing the array like a pointer because it's a memory address. That might be because you didn't use the square brackets to pick a particular element of the array, but who knows? I'll let you play around with whatever you're working on. Claude's saying %c is one character at a time, %d is one number at a time, and one number could be made up of multiple characters. %lf is one floating point number at a time, and that also could be made up of multiple characters. So it'll take one unit, and it will, whatchamacallit, it'll take one unit of thing that matches the pattern and use it. Tom's asking if that %c thing that we did before, will that work with whatchamacallit? Will that work with the enter key? And I think it did here, because this is the test. Is that the test that we did, or is this the test that we did? Either way. No. Oh yeah, no, it did. So this is the one that we did where we were doing %c, and it definitely still read the enter key. Because I don't think there's anything here that didn't. Yeah. So scanf with %c and getChar are nearly identical. They're not identical in that their function output is different, because getChar's function output gives you a character as the function output. Scanf %c will tell you how many characters it read in as its function output. So they will act differently. Programmatically, they're very different, but the side effect of them reading in a character is the same. Okay. I think I should wrap it up there. Thanks all for coming. And I will see you tomorrow being Thursday afternoon, for our next lecture. Alright. Goodbye. Oh, wait. Someone had a question. Charles is saying, you missed the freefall stream last week, but how bulletproof does the assignment need to be? Do we need to verify the validity of every single input? Charles, we don't need to verify the validity of every single input apart from the points in the spec that say to. So the spec will say which things are valid and invalid input, and there'll be some information there that says things like, we're never going to give you characters as input. We're only going to be giving you numbers as input, but we might give you numbers that result in something that is incorrect. So what we're doing is we're not making you check whether something is a digit or not, because we haven't taught you how to do that. But we will say, for example, this is the same example I've used a couple of times, that we may give you a line that is invalid because it it goes outside the screen. So there's the map, and there's a line that tries to get drawn outside the box, and if it gets tries to get drawn outside the map, sorry, then the whole thing shouldn't be drawn at all. So little things like that. Yeah. Okay. Thank you, everyone. And I will see you Thursday. Thursday, we're going to keep going with characters. So don't worry that I kind of cut it off halfway through there. We'll keep going with the characters. We're going to join the characters up into strings. Charles, that was Chicken, but Chicken was going the opposite direction. Chicken was asking to be let through the door away from me rather than towards me. So I apologize. You'll have to wait for Thursday to see Chicken again. Okay. See you all soon.